remember correctly. But it has things like quantum numbers. We're not doing those. We don't have anything like that. You don't have to worry about it. So. Yeah, the old version, they used to do quantum numbers. And they used to do a lot more with math, like calculating the wavelength and those kinds of things. But anyway. Okay, so if we were to talk about our periodic table. Okay, so it's not enough to be able to say this is where it is on the periodic table and say that that's why. Like, that's not a reason behind where it is, but it's a good thing for us to use to kind of base ourselves on where we want to go. So when we're talking about atomic radius and we're looking at ionization energy, those are the biggest ones to do. And I said if you could kind of remember atomic radius, all the other ones are going to be based on the atomic radius. So two big rules that we want to remember, that as we go down the table, our atomic radius increases. And the reason behind why this is going to be increasing is because you have a greater number of energy levels, which creates less shielding and fewer attractions between the outer electrons and the nucleus. So basically what that means is a decrease in effective nuclear charge due to shielding. So let's kind of review what those words mean. So nuclear charge is just how many protons do you have? And protons have a positive charge. So the more protons you have, the stronger the attraction is going to be. That's just as simple as that. When we talk about this thing called the effective nuclear charge, what we're looking at is the comparison between our number of protons and where our electrons are located within the rings around it. Rings is kind of an inappropriate word for it, but you know what I mean. And so when we go to look at that, we want to know how many filled energy levels are there? Because if our protons are here in the nucleus, each level, like if we go back to Jack's analogy that he used about like putting on a coat over the nucleus. And so the first coat just kind of keeps you a little bit warm and blocks those electrons a little bit. And the further out we get, the more electrons we get that are in a filled orbital, the more protection the outer electrons have from that nucleus. And so that's what we're talking about when we're talking about that shielding. And so our effective nuclear charge is kind of a balance between those. The more shields we have, the less impact that nucleus has, even though we're also going to be getting more protons. Does that make sense? Questions about that? Okay, that one tends to be the easier one because it kind of goes with what you would think. But remember, atomic radius gets bigger as you go this way across the table. So we have fewer protons here, more protons here. And so people get confused and they want it to be the opposite way. But if you remember, within a row, they're going to have the same amount of shielding. So the shielding stays the same. And what you're doing is as you increase those protons, you're able to increase your nuclear charge because our shielding maintains itself, and now we're just getting more positives there in the center. So those positives, like we said, have that attraction for the outer electrons, and that pulls those electrons in. So in here, we increase our radius.
Janet Fisher, please dial 2000 from any phone.
Because we have an increase in nuclear charge. Does that make sense? Okay. So questions on that one? Nope. So then our ionization energy, that's how much energy it takes to remove an electron. So it's always about taking away an electron. people get that mixed up with thinking it's just making an ion in general. But we're just talking about removing electrons. So the bigger the atom is, the more difficult it will be. Smaller the atom is, the more difficult it will be to remove an electron. So the bigger it is, the less energy it takes to remove an electron. And so if you remember, we're way down here on the list. Our electrons have a lot of shielding. So those outer electrons do not have a very large attraction towards that nucleus. And when that nucleus, if something has the energy available to remove that electron, it's going to go ahead and do it. Now remember, it still takes energy. It will always take energy to remove an electron. It's just going to take a lot less energy to remove this electron than to remove that electron. Okay, and so then increasing radius, remember, it still got bigger this way because we have the smallest nuclear charge on this side. So those electrons aren't attracted they aren't attracted as strongly to the nucleus as the ones on this side. So it's going to take less energy to pull that off. And so remember, as we go across, our energy increases. And the most often way we see ionization energy is within a row. And they like to ask that question about which column is your electron or your atom likely to be in based on those ionization energies. And so I'm just going to make up numbers, but if they gave you like your first ionization energy, they were looking at first ionization energies, and then it went to like, so it was 100, 200, 300, 40,000. Okay, so we had this huge jump. So removing 3 electrons took some energy. Removing that 4th electron took an extreme amount of energy. So that tells me that this electron was probably one of the core electrons. So this atom had 3 valence electrons. So this would be a great multiple choice question where they would give you like, is it sodium, magnesium, aluminum, or phosphorus? And they would have to pick which one it could be. You guys look like you're looking. Sodium, magnesium, aluminum, silicon, we could say. So which would you guess this would be? Aluminum would be a winner because aluminum has 3 outer electrons. And once you remove those 3 outer electrons, then you start pulling away from the core. And so that kind of represents what we're doing here. Does that make sense? You guys look like you're thinking about that a little bit. I'm going to explain that again.
So if you're removing 3 of them and then the 4 electrons, they're not all fixed ionization.
Right. But like they would be comparing, they'll be asking about like, another good way to say it would be if they wanted to compare aluminum to sodium, and they would ask you like, which is going to have the lower first ionization energy, something like that. Okay, so radius. Oh, I want to talk about ionic radius for a minute.
So the amount of ionization energy used to be this one was growing based on the level not will ever account that.
So let me restate your question, partly for internet, partly to make sure I understand. So are you saying the energy level never impacts your ionization energy? Is that what you're asking?
No, it will always, but like everything else doesn't matter.
Like what other things would you think
Right.
of? What are you thinking doesn't matter?
Like you know how like magnesium, for example, isn't like it has the outer orbital has 2s.
Right?
So if aluminum, you know.
Oh, because like aluminum has one of its electrons in the p orbital
Yeah.
versus magnesium, they're both in the s.
Yeah.
Yes, that definitely can play a role in it. Where you would see something like that is the AP would give you some information. And they could say, look at the second ionization energy for magnesium and the third ionization energy or whatever. Look at these ionization energies for magnesium and aluminum. And they would say, explain why the trend is that aluminum decreases a little bit from where magnesium is. Okay, if we're looking at their energies, that aluminum's first ionization energy, it's going to pull from that p orbital, and so it's going to lose a whole orbital. So it's going to be a little bit easier to remove aluminum's first ion or first electron than to remove magnesium's first electron because you're pulling it from a filled orbital. So that kind of bucks the trend a little bit. So they wouldn't expect you to come up with that on your own, but if they gave it to you, you would need to explain it. And that's a great question. Does that make sense? Okay. So then cations versus anions. So remember, anions are negative and cations are positive. So still kind of base it on your atomic radius. But if we are a positive electron or positive ion, not a positive electron, positive ion, that means we've lost the electrons, right? And so keep in mind that over here, we've got our atomic radius. And so we're moving down to a core level. So we're decreasing our shielding. But did we change anything with our protons? No. So we have less shielding, but still a larger number of protons. So our atom's going to get even smaller here because you've increased your nuclear charge. Whereas over here, your your anions, now we've got extra electrons. We've got a filled orbital, so the same shielding as we had before, and the same number of protons as we had before, but now we've got these extra electrons. And so that causes your electron cloud to get a little bit larger. And this gets larger because we have increased electron repulsions here. So smaller because it's an increase in nuclear charge. I would anticipate those being the big four, big three. I guess I was counting those as two separate ones. But atomic radius, ionization energy, and the ionic radius are the ones I've seen asked about the most often. But, we talked a couple times about polarizability. That's not going to be dealing with atoms or ions. We would deal with those with compounds. And remember, the larger it is, the more polarizable it is. That's a good one just to talk about as much as we can. What questions do you guys have? I feel like everybody's not quite awake yet. Coulombic attractions. We didn't say that word one single time. That's two words. But either way, we didn't say it. We should talk about Coulombic attractions. And so anytime you want to talk about Coulombic attractions, along with like the idea, kind of goes with your nuclear charge, the concept of your protons and your electrons. If you want to, you're welcome to come sit in the back if you want to. It's not a big deal. I didn't take the time to write a message today. So when we have an increase in nuclear charge, that's really telling us that we have our Coulombic attractions are greater between our compounds. And so anytime you have the ability to talk about the relationship between a positive charge and a negative charge, you want to talk about your Coulombic attractions. So maybe it's a proton to traveling electrons. Maybe it's the protons of one atom to the electrons of an accompanying atom that they're trying to bond together. Could be to a cation and an anion. Doesn't matter, but just talk about the reason why two things are going to be attracted together is always going to be because of those Coulombic attractions. So the more you can use that word in nuclear charge and electron repulsions effectively, the better your life's going to be.
Did you say Coulombic attractions increase the nuclear charge? The increase of
The effective nuclear charge, the increase of your effective nuclear charge, because you're going to have greater pull on your protons to your electrons when you have more nuclear charge. So that's going to pull them closer together. That is true. What other questions do you have? Do you guys remember what lattice energy is? Okay, lattice energy, for those of you that are shaking your head, no. It's basically a way of quantifying how much energy is within an ionic lattice, which is that crystal structure. So if I'm we're better at drawing, that would make everybody's life better, but I'm not. So it's just as a thing that we have to all accept. And so here, this is what we call a lattice crystal. So the amount of energy that is within there is going to be our lattice energy. And so that's based on two things. It's going to be based on the size of your atoms, and it's also going to be based on the charge, the magnitude of your charge. So like if it's a +2 ion versus a +1 ion, NaCl versus MgCl2, this is going to have a greater attraction, so a stronger lattice energy. And then the smaller they are, the closer they're able to get together. So that will have them have greater Coulombic attractions and increase the energy as well.
Are ionic compounds polar?
Ionic compounds we would not define as polar. We would just call them ions. So they have a complete charge to them, but they can be attracted to something that is polar. So a bond between a molecule, like let's say water, that is polar, and an ion like magnesium ion is going to be a lot greater than a bond between two water molecules. Because now you've got a polar molecule being attracted to an ion, they will be a lot closer together, the greater an increase in Coulombic attractions because your ion's closer to that nucleus. Does that make sense? I'm not showing half my board. Okay, what other questions could we possibly have? While you guys think I'm flipping through here to see if there's anything that jumps out at me as something I should talk to you about. They asked for hints on how to draw Lewis structure quickly, but I didn't remind anybody how to do Lewis structures. Do you feel comfortable with knowing how to draw Lewis structure? We comfortable with the idea of bond length versus bond energies? Bond length versus so bond length, the more bonds you have, like a single bond versus a double bond versus a triple bond. The more bonds you have, the shorter the length. And so the shorter the length of your bond, the more energy it's going to take to break them apart. And that's kind of something we want to do. And then we learned how to calculate that bond energy, but I don't think that will be a big thing on your test. It'll be more talking about like heats of formation and using Hess's law and using calorimetry, which we'll talk about next week, but those kinds of things. Do we have to know a resonance structure? Maybe, that could be fair game. A resonance structure is just a way of drawing a compound that's one Lewis structure isn't enough to represent it. So if we had, let's say like nitrate. So nitrate here, that double bond doesn't stay stuck with one oxygen. It's not like tied to that oxygen. It actually has the ability to travel between each of these. And so to properly draw that, you would have to draw 3 different Lewis structures.
Mrs. Brewer, please dial 2000 from any phone.
I don't have enough room. And you have to actually represent all 3. Now, the likelihood of them asking you to draw 3 Lewis structures seems pretty silly because it just takes a long time. There's a lot more questions they could ask you, but it could be an opportunity for them to ask you which one's most likely to show resonance. And they give you a series of compounds and you'd have to pick them out. So you would then have to pick based on your Lewis structure. So that's drawing potentially 4 different Lewis structures. And that would take you a long time. So you want to be able to quickly look for things that you know are going to have to double or triple bond in there. And so nitrate's a really common one to use. Like nitrogen in general, because it only has 3 locations to put electrons, and it's high on the periodic table. Because remember, above the 3rd energy level, they have kind of more limitations to what they can do. And so it often will cause it to have a double bond. So carbonate, nitrate. Those guys are good examples of things to think about. So if you have a double bond one place and nothing, just single bonds other places, then they can travel around. That was a long question answer. I'm sorry. You just wanted a yes or no. I don't know. That's really all I have. They have all the functional groups here on page 172. Any of the functional groups. As I've said a few times, I don't think they're going to have you name organic compounds anymore. I think they will just be giving you organic compounds, and then just the more you know about them, the more comfortable you'll be with them. Okay, do you guys want to call it a day, or do you want to talk about intermolecular forces? Those would be my suggestions, one of those two. Call it a day.
Sure.
Okay. Bye, Internet World.